Welcome to Lecture 1, Introduction to Weather and Climate. The reading for this lecture is Chapter 1 in the Ahrens book, pages 1 through 25. So in this lecture you will be learning about what weather and climate are, how you define them, how they're different from one another, and then we will be going into important properties of the atmosphere, especially its vertical structure. And then we'll be looking at an overview of weather. I think that it would be worthwhile in this introductory lecture to provide some definitions that are important as we go forward in the class. So how would you define weather, first of all? I'm not asking you to describe it, but how would you define it? If someone asks you, what is weather? Okay, what would you say? You can define weather as the state of the atmosphere at a particular place and time. And it's highly variable, changing from hour to hour, day to day, year to year. Weather is basically the here and now of the atmosphere. Okay, it describes what the atmosphere is like at a certain location at a certain or given time. How is that different, though, from climate? Climate, on the other hand, is the accumulation of daily or seasonal weather events over a longer time period. Okay? It represents a long-term average of weather, but it does have to include the extremes. So, while weather is more local in a geographical sense and short-term in a temporal sense, climate is more regional, it turns out, in a geographic sense, and longer, or long-term in a temporal sense. And it does represent a long-term average of weather, but it still takes into account the extremes in order to come up with that average. For example, the record highs, temperatures, the record low temperatures, the record precipitation events. There is a famous quote by Mark Twain: "Climate is what we expect, weather is what we get." Okay, if I pronounce that right, I can kind of make it rhyme. Now, what do you call the study of weather? Meteorology, right? Not weatherology. And it still happens today where I'll tell people that I'm a meteorologist or I've studied meteorology in college, and they will start asking about meteor showers, okay, space. So the meteor in meteorology does not refer to meteors from space, but it refers to actually hydrometeors, which are basically falling particles of either liquid or solid water in the atmosphere. Climate study, the study of climate, has a more intuitive name. It's called climatology. Okay, so as you see, meteorology and climatology represent the study of weather and climate respectively. But they are each components of atmospheric science and are dealt with in this course. So meteorology and climatology both examine the atmosphere, that thin layer of air that we need to breathe, contains all the weather. But the differences between the two is in the scales, both geographically and temporally. Now, how would you describe weather? What variables does weather incorporate? Well, perhaps the most obvious one, or the most talked about one, or the one that comes to mind first, is temperature. How hot or cold it is outside. Okay, it's very important. It determines what you wear, right? How you dress. Determines whether you get sweaty easily, or if you feel that you have to eat a lot more to satisfy your hunger, right? If it's colder, you tend to have to eat more because your body has to use more energy in the cold. There are other variables describing weather. And by the way, temperature, on a molecular level, it's more complicated than just how hot or cold it is. We'll be examining exactly what temperature means on a molecular level later on. What else describes weather? Humidity. Okay, and the most common humidity variable in the general public is relative humidity. There are many humidity variables. There's dew point, you may have heard of. There's others like specific humidity, mixing ratio, absolute humidity. We'll be talking about them later in the class when we talk about humidity concepts in chapter 4, or FO, if you prefer. But this one is what you see on your Weather Channel app, or if you have an iPhone and you have the default Yahoo Weather app. Okay, this is the one you see on the news, on the local forecast, on the Weather Channel, right? And what is its total range? What's the lowest possible relative humidity that can exist at any time in a location? Give you a clue, it's expressed as a percentage. The lowest possible relative humidity is 0%. If that's the case, the air is 0% to capacity with the amount of water vapor it can hold at that temperature. Basically, it doesn't have any water vapor in the air. If the relative humidity is 100%, the air has as much water vapor or moisture, if it helps you, as it can hold at that temperature. So the range is 0 to 100%, and to remember the range for relative humidity, you can just think of Drake's song, 0 to 100. What else describes weather? How about how windy it is? And there's two components of wind, right? What are they? There's wind direction, the direction from which the wind is blowing. Turns out in meteorology, we define the wind direction not by the direction the air is moving toward, but the direction the air is coming from. So, for example, a west wind would be coming from the west, blowing to the east, 180 degrees from the direction it's coming. There's also wind speed, how fast the air is blowing. And both of these are very important in describing the wind. Direction will determine if you're driving a certain direction, the wind direction determines whether the wind comes at your vehicle, the wind blows at your vehicle from behind, the wind blows across the road, and so on. And the speed, is going to make the difference between whether there's small eddies of leaves on the ground, trash cans are being blown over, or roofs are being destroyed, right? And another example for the importance of wind direction and speed is when you fly. If you fly, let's say, across the country, let's say you're going from San Jose to New York City, flying across the country from west to east will be about an hour faster than flying from east to west. Okay, you may be familiar with this. And the reason has to do with the jet stream. Jet stream is a belt or region of very strong winds in the upper atmosphere. And it generally blows from west to east. It can meander There's loops in it, but it generally blows west to east, not east to west. So pilots flying from west to east get an added tailwind that helps them travel faster, whereas the pilots traveling from east to west across the U.S. have to encounter and deal with a headwind. It slows them down, and that's why also there tends to be more turbulence. All else being equal, on a clear day, not talking about thunderstorms, but generally it's a little bumpier to fly from east to west than west to east. Finally, we have cloud cover, which is another variable describing weather. Are there nice clear blue skies and sunshine? Or is the sky overcast in the morning, making it hard for you to wake up and get your day turned up? Remember, climate represents a broad average of the weather for a region over a much longer time scale. Weather is on the time scale of minutes, hours, days, months. But climate also on the time scale of decades, centuries, thousands of years. So when you want to define climate for a region, you have to be looking at least tens of years of data, if not hundreds to thousands of years. Okay. By the way, if you want to talk about climate change, you can't just look at a few years of data. That's weather. Okay. You can't see that the temperature, say, decreased for the world from one year to the next and say, oh, there's global cooling. You have to be looking at least decades, and if you do that, you'd see there's a clear warming over the 20th and into the early part of the 21st century for the world. We'll talk more about climate change later on in the class. There's different types of climate. For example, the Mediterranean climate is characterized by relatively hot, dry summers and cool, wet winters. And Sacramento, California, the capital of our state, with a population of about 500,000 people, the metro area, including Citrus Heights, Roseville, is even larger. Well, Sacramento has this climate. How would you see that? Well, you'd have to look at climate data over tens of years, at least, that show it tends to be hot and precipitation free in the summer, and cool, not super cold, and wet in the winter. Okay? We can see that if we look at climate data. Here is data for the city of Sacramento. Source is weather.com. And on the left, you have average monthly high temperatures in orange, or basically the white numbers in the orange circles. And the numbers in the blue circles are, as you might surmise, average monthly low temperatures. Okay, we have the 12 months of the year. On the right here, this figure shows average monthly precipitation, okay, for the 12 months of the year. And by the way, the temperatures are in degrees Fahrenheit, which is good for us Americans, right? And the precipitation is represented in inches. Now, Sacramento rarely, very rarely experiences snowfall. Okay? Maybe once every 10 to 20 years, if that. So when you talk about average precipitation in Sacramento, you're generally talking about average rainfall. You can use the two terms kind of interchangeably because there's very little frozen precipitation in Sacramento. So it's important that when you analyze these figures, you are able to read them correctly. It's important when you analyze these figures that you pay attention to the labels to understand how to read them. Now, can we see evidence that Sacramento has a Mediterranean climate? Well, we said that Mediterranean climates were characterized by relatively hot, dry summers, first of all. And I think you'd agree that these summers in Sacramento are hot. Look at the average high temperatures in summer. When does summer begin? In the northern hemisphere on the June solstice, June 21st about. And so summer ends on September 21st, the September equinox. So the 2 months of the year that are completely encompassed by summer are July and August, right? Those tend to be the 2 hottest months of the year in the northern hemisphere. In general, San Francisco actually has its warmest month of the year being September. In July and August, though, in Sacramento, average high temperatures are in the low 90s, okay? And it's important to remember that these are only average monthly high temperatures. This is climate of Sacramento, what you'd expect. Remember Mark Twain's quote, what you'd expect. On average in Sacramento in July, you'd expect average high temperatures in the low 90s. But actual daily high temperatures can vary significantly over that. So, in general, Sacramento gets numerous 100 plus degree Fahrenheit high temperatures each year, okay? Perhaps a 2 to 3 dozen or so. And occasionally, Sacramento will get near 110 degrees Fahrenheit, okay? On the other hand, there are days in July and August. There are days in July and August in Sacramento where average high temperatures barely make it out of the 70s, okay? And the average lows in July and August in Sacramento are in the low 60s, okay? It does cool off nicely at night in the summertime. You know, in much of the country, the eastern half of the country, when it gets hot in the day, it tends to stay hot overnight, okay? Like, so in places like in the Northeast, like New York, even Boston, places in the South, like New Orleans and Miami, it can stay in the 70s all night, even sometimes barely make it down into the 70s, okay? By the way, you will notice a greater diurnal temperature range, that's basically daily temperature variation, in Sacramento in the summer versus the winter. Even in June and September, which are not completely encompassed by summer, high temperatures on average are in the upper 80s. By the way, these average high and low temperatures and average month and precipitation amounts, and these are all values for the month, are based on about 30 years of data. The 1981 to 2010 climatological averages. That's 3 decades of data. Now, can we see that it's relatively dry in the summer in Sacramento? Well, let's look at our 2 summer months, July and August. Those are astronomical summer months, okay? How much rain in Sacramento or precipitation in Sacramento in July on average? Big fat 0, okay? August, 0.03 of an inch of precipitation on average in Sacramento, okay? It's almost unheard of to have rain in Sacramento in July and August. Rarely, monsoon moisture will move into Northern California from the desert southwest and bring thunderstorms to Sacramento. So it does happen. It's not completely unheard of. And even in June and September, kind of the borderline months of summer, still extremely little precipitation is found. Now, our second part of the Mediterranean climate was about winter. Cool, wet winters. Is it cool in Sacramento in the wintertime? Well, if we look at December and January, even though winter doesn't start astronomically until about December 21st or 22nd, the two coldest months of the year in the Northern Hemisphere tend to be December and January. Not always, but for most cities, that's the case. And it's true for Sacramento. Average high temperatures in December and January are at 54 degrees Fahrenheit. Average low temperatures for those 2 months are in the low 40s, right? And several days a year, Sacramento experiences freezing temperatures at night. That is, the low temperatures get down to 32 degrees Fahrenheit or colder, occasionally down into the 20s. And for a place like Sacramento, which is in the middle of the Central Valley, that's a big issue because of all the crops that are grown there. Now, we said it's wet in the wintertime. Can we see that? Well, in December, January, February, and even March, average monthly precipitation is above 3 inches. Okay? That's more than 1/10 of an inch per day on average. Okay? Compare that to the summer months when there's basically no precipitation. In fact, it's very clear how the precipitation is very little in the summer, and most of it appears to occur in the winter time. Look at the graph. And if we added up all these monthly average precipitation amounts over the course of the year, we'd find Sacramento's yearly average precipitation is 20.37 inches. And you could do some more math and discover that 14.26 inches, or 70%, more than 2/3 of the annual total, occurs between the months of December and March. And those are the winter months, right? In the sense that winter begins in December and ends in March. So, hopefully you are seeing how Sacramento has the Mediterranean climate. Now, let's kind of switch gears and look at some more extreme weather events here before we go forward in examining the atmosphere. You might have heard of the large snowstorm in New York City earlier this year in January. It was the second biggest, in terms of total amount, biggest snowstorm in New York City history. Okay? Just behind the February 2006 snowstorm. So, the January 2016 snowstorm, or blizzard as it's called, that's a snowstorm with strong winds and great amounts of the fluffy powder. That snowstorm had over 2 feet in Central Park. That's where these New York City measurements are taken. There's other weather stations in New York City, but that's where the default city measurements are taken, if you will. Okay, if you typed in New York on the Weather Channel app or searched for it, generally the default data you'd get, okay, is for Central Park. January 2016 snowstorm had 26.8 inches. Mind-boggling, right? That's close to their average annual snowfall. And it missed out on being the biggest snowstorm ever for New York City by 0.1 inches, okay, 1/10 of an inch. And if you're wondering about, well, ever, does this mean throughout the Earth's history? Well, not quite, but the recorded data goes back to the late 1800s, okay? So this is still very significant. By the way, 3 of the 5 largest snowstorms in New York City have occurred in the past decade or so, which is interesting. Now, I do have some photos of that January 2016 snowstorm. It not only affected New York City, but it affected further south, okay? Jersey City, New Jersey is just on the other side of the Hudson River from New York, the Big Apple. It's literally just a few miles, okay, so it's very close. And Aberdeen, Maryland is about an hour and a half or so outside of Washington, D.C., okay? And there are some photos, okay? The two from Jersey City are courtesy of my brother who lives there. And the one from Aberdeen, Maryland is from my uncle who lives there. So here's a photo my brother took of a police car in Jersey City, okay? And you see the effect of the great amount of snowfall, right? It would be hard to drive this police car as is, right? You'd have to do a lot of shoveling in order to enable it to be driven. And here's another car completely submerged by snow, right? Well, almost, okay? You can see the mirror here and part of the frame, little portion of the frame. Sometimes the wind will blow snow into piles and creates what's called snow drifts. And here's a picture from my uncle in Aberdeen. And he basically had shoveled his driveway. Took him a long time to do it. But he went and shoveled his driveway, okay? And you see all the snow on it, basically the lawn. And if you look closely, you can see it's a great amount of snow, right? It would go up to past his knees, right? It looks like. So, the Bay Area gets weather too. We don't really get blizzards, but we can get very strong winds. We can get heavy amounts of precipitation, okay? Here are some peak wind gusts back from January 31st of this year when we had a strong wind event. And these the strongest wind gusts on this list occurred in Point Reyes along the Marin coast, where the winds were clocked at 60 miles per hour. Okay, that's getting close to hurricane force. Ocean Beach had a wind gust of 54 miles per hour. You see wind gusts in multiple locations: Concord, Monterey, San Francisco, okay, Mount Tamalpais and Marin and Half Moon Bay getting above 40 in the 40 to 50 mile per hour range. Even Napa had a wind gust of 42 miles per hour. The same wind gust occurred in Livermore. And even in San Jose, wind gusts were at 36 miles per hour, just slightly less than tropical storm force winds. You also may have heard of the August 2016 flooding that's been going on in Louisiana. Historic flooding, okay? Some places were picked up more than a foot of rain in about a day or so, okay? Some places experienced what's called a 1 in 1,000 year event, where the amount of rain they saw in about a day or two was equivalent to that which occurs once every 1,000 years. So that just shows how rare it is and how unprecedented it was, and hence you can understand why there was a lot of flooding from that great amount of rainfall occurring in a short time period. There's a Ryder truck driving through a submerged road. And here's a picture from a helicopter showing a submerged neighborhood, okay? There were people rescued, actually over 1,000 rescued in Louisiana when this photo was taken. It does bring back memories of Katrina, which occurred about 11 years earlier, okay, where people were being rescued from their rooftops. All right, now, we've talked about what weather and climate are, so hopefully you understand the difference. And we've been looking at some weather events. Let's start talking about what the atmosphere is composed of. Okay? Do you know what is the most abundant gas in Earth's atmosphere? Or what's the most common gas in Earth's atmosphere? Well, it's nitrogen. Might surprise you, but there's more nitrogen in the atmosphere than oxygen. We'll talk about how much in a minute. But oxygen is the second most abundant gas in the atmosphere. So the Earth's atmosphere is a very thin, with respect to the Earth, solid Earth, gaseous envelope comprised mostly of nitrogen and oxygen. And nitrogen and oxygen tend to not, the atoms don't like to be alone in the atmosphere, so they bond together with a buddy of the same type. So nitrogen exists as molecules, two nitrogen atoms clustered together. Same with oxygen. That's how it appears in the atmosphere. There are small amounts of other trace gases in the atmosphere, such as water vapor and carbon dioxide. Water vapor is an important gas because it not only contributes to humidity, how sticky it feels, right? If the air is very humid, it can make your hair frizzy, it can make your sweat just build up on your skin and not evaporate, right? If the air is very dry, there's low humidity, your lips can get chappy, your nose can bleed, right? Your hair can also feel the effects of low humidity. But basically, humidity is dealing with water vapor. The more water vapor in the air, the higher the humidity, okay? Water vapor is also important because it's necessary for clouds to form. It's also a greenhouse gas. And carbon dioxide is a very important greenhouse gas that we'll be talking about. And carbon dioxide concentrations now are higher than they've been in 800,000 years, probably longer. Okay, they're at unprecedented levels because of the enhancement of Earth's greenhouse effect. We'll talk about how this is happening and why it's important with respect to global warming. Now, gases are not the only materials in the atmosphere. There's also clouds of liquid water and ice crystals. Although the atmosphere extends upwards for many hundreds of kilometers, almost all of the atmosphere lies within a mere 30 kilometers or 19 miles of Earth's surface. Okay? If Earth were to shrink to the size of a large beach ball, its inhabitable atmosphere would be thinner than a piece of paper. But this thin blanket of air is very important because it provides the oxygen we need to breathe, and it constantly shields the surface and its inhabitants from the sun's dangerous ultraviolet radiation, as well as the onslaught of material from space. Here's a nice picture showing how thin the atmosphere is. Okay, here's a picture showing a sunset in space, courtesy of NASA, and you get a sense of how thin the atmosphere is. You see the lower atmosphere being light, very bright colored, maybe mixing with blue, and as you go higher up, the blue becomes darker. Eventually, the color turns black of space. "99% of the Earth's atmosphere is within about 19 miles of the surface. 90% of the Earth's atmosphere is within just 10 miles of Earth's surface." And for some perspective, the radius of Earth is about 3,959 miles. 3,959 miles. So close to 4,000 miles, roughly. So compare how 99% of Earth's atmosphere is within about 20 miles or less than that, 19 miles to the surface. Whereas the solid Earth has a radius of about 4,000 miles. That just gives you perspective of how thin it is. Now, what's it made of? We know it's mainly made of nitrogen and oxygen gas. We're going to start talking about how much, what percentage of the atmosphere is composed of these gases, these two most abundant along with others. Well, nitrogen makes up about 78% of the atmosphere, and oxygen makes up 21%. So you do notice that these two gases alone make up 99% of the atmosphere. And this is basically by volume of dry air. We'll talk about this, but water vapor in the atmosphere is highly variable. It's a function of temperature. In the cold polar regions, water vapor content can be close to 0%. But in the tropics, where there's a lot of evaporation off the oceans, because they're very warm, water vapor concentrations can get near 5%. But if you're talking about dry air and collecting water vapor, which is very variable, not 78% of the atmosphere will be nitrogen, 21% will be oxygen. And the proportion of these gases is fairly constant up to 80 kilometers or 50 miles above the surface. Here's the table from the book, table 1.1, showing the various gases present in a volume of air near the surface. At the surface, there's a balance between the output and input of these gases, so the concentration is constant. That's true for the permanent gases. But variable gases have been changing in concentration over time. Okay. So if you look here at the permanent gases, here's nitrogen and oxygen making up 78-21% of dry air by volume, respectively. Argon, which exists as a single atom, makes up nearly the remainder of dry air, okay, 0.93%. And then you see some more permanent gases, neon, helium, hydrogen. Helium and hydrogen are the two lightest elements, not in that order. Hydrogen's the lightest, and make up a very small percentage of the atmosphere. We talked about the variability of water vapor in the atmosphere. Carbon dioxide has increased in the atmosphere greatly. Now, this book actually the table from this book is from 2007. This is from the 5th edition of the book. The table is from the 5th edition, published in 2007. Back then, CO2 concentrations were 0.038% by volume of air. And that's equivalent to 380 parts per million. A part per million means that 1 part per million means that out of every million air molecules, 1 would be a CO2 molecule. Or 1 would be that particular molecule. So 380 parts per million for CO2 means that out of a million air molecules, 380 are CO2. Carbon dioxide. And another way to think of that is for every million units of volume of the atmosphere, say 1 million gallons of the atmosphere, there would be 380 gallons of CO2. You know how a percentage is 1 in 100, right? 80% means 80 out of 100. Well, 1 million is 1 in 1 million. Methane concentrations have increased in the 20th century into the early part of the 21st century. As well, they're now up to near 2 parts per million. Nitrous oxide concentrations have increased. Carbon dioxide, methane, and nitrous oxide are all anthropogenic or human-induced greenhouse gases. In fact, the 3 most abundant greenhouse gases that are being put into the atmosphere and increasing in concentration. These are greenhouse gases that come from human means. Ozone exists in the lower atmosphere at concentrations of about 0.04 parts per million, or 0.0000004%, very small. But ozone is more important in the stratosphere, the second layer of the atmosphere from the ground. We'll be talking about the 4 layers of the atmosphere and their properties. Their stratospheric concentrations can get between 5 to 12 parts per million, and that's where we find the ozone layer, which protects us from harmful UV radiation. Particles in the atmosphere can be made of solid or liquid, like aerosols, dust, soot, salt. CFCs make up an extremely small amount of percentage of the atmosphere, almost non-existent compared to the other gases, and yet extremely important because the CFCs are what is we're breaking up the ozone layer. You might have heard of the ozone hole over Antarctica. We'll talk about that, but the CFCs, chlorofluorocarbons, were being released from aerosol sprays, cleaning solvents, old refrigerators, and breaking up the ozone, O3, into monatomic O and diatomic O2 oxygen. And so that was allowing more ultraviolet radiation to reach the surface. And we care a lot about that, right? Because if there's too much ultraviolet radiation being absorbed by your skin, what can happen? Sunburn, skin cancer. Okay, so we talked about how carbon dioxide, methane, CFCs are also found in the atmosphere along with ozone, aerosols, those microscopic solid or liquid particles suspended in the atmosphere. When you see pollution, you're seeing aerosols, okay? So when you see that haze or brown sky, and if it's really polluted, it can be hard to breathe, especially for people with asthma. You're looking at aerosols. And clouds, of course, make up the atmosphere. We'll be talking about clouds in chapter 4. And when we do that, you'll be able to look at a cloud and determine its name, where it is in the sky, whether it's low, middle, or high. That rhymes. If it's going to produce precipitation. If it's a cloud that tends to reflect sunlight, or if it's a cloud that tends to absorb Earth's outgoing heat. For humans, ozone at high altitudes in the stratosphere is good. It protects us from ultraviolet radiation. It's not only good for humans, but also for plants. But ozone in the lower atmosphere, in the troposphere, which is the lowest layer of the atmosphere where we live, is bad because there it can combine with smog and can cause irritation to the eyes and irritation to the lungs. No bueno. We talk about carbon dioxide as being an important greenhouse gas. Here's a nice figure from the book showing the sources of carbon dioxide in gray. Those are processes that put it into the atmosphere. And the sinks of carbon dioxide in red, processes that remove it from the atmosphere. So carbon dioxide can enter the atmosphere from the burning of fossil fuels, coal and oil for power generation. Coal and natural gas for power generation. Oil or products made from oil like gasoline and diesel for energy for transportation. There's a lot of products made from oil. Plastics, basketballs, perfume, toothpaste. When you burn them, it puts CO2 into the atmosphere. Volcanoes can emit CO2, as can the burning of plants or trees. Deforestation, the burning of forests, is done for agricultural purposes, to make room for crops or buildings. That puts CO2 in the atmosphere. When the plants breathe out, respiration we call that, puts CO2 in the atmosphere. We mentioned deforestation, the burning of forests. Soil decay is a source of CO2. And there is a great amount of CO2 in the upper ocean. In fact, we're very thankful for the upper part of the ocean's ability to absorb CO2. If it wasn't for the ocean's ability to take in carbon dioxide from the atmosphere, CO2 concentrations could already be near 1,000 parts per million, 2.5 times what they are now. And the temperatures for the world would be much higher already. Now, there's also ways to remove CO2 from the atmosphere, thankfully. Photosynthesis from plants is one way. Plants take in carbon dioxide, and they use that along with water and energy from the sun to produce carbohydrate or sugar called glucose for their nourishment. Oxygen is produced as a waste product. Carbon dioxide can also dissolve directly into the ocean's surface water as phytoplankton take it in. And marine life in the deeper ocean can also take in CO2. Estimates are that the ocean contains more than 50 times the total atmospheric CO2 content. Now, CO2 concentration has been going up. This figure, called the Keeling curve, clearly illustrates that. It's named after the scientist who helped these measurements get underway. The measurements are taken at Mauna Loa Observatory in Hawaii. And higher readings have occurred more recently. Okay? When the CO2 concentrations began in March 1958, the levels in the atmosphere were about 315.71 parts per million. As of March 2016, CO2 concentrations have increased to 404.83 parts per million. That's a 28.2% rise in 58 years. The gray bar, which you see oscillates, is monthly CO2 concentration, and the solid blue line represents the yearly average CO2 concentration. You might be wondering, why is there this oscillation or wobble in the CO2 concentrations? You know, when the measurements first began, over the first few years, scientists wondered if the instrument measuring CO2 was malfunctioning. But it turns out the reason has to do with the seasons. Higher readings of CO2 occur during the winter time and into the early spring as the plants have die and release CO2 into the atmosphere. And the lower readings occur in the summer, because in the springtime the plants are growing and taking in CO2 during photosynthesis, causing the CO2 levels to go down. Now, carbon dioxide, or CO2, is an important greenhouse gas. The more CO2 in the atmosphere, the more of Earth's outgoing heat, which is in the form of infrared radiation, is trapped before it escapes to space. And the warmer the Earth's surface, all else being equal. In fact, global average surface temperatures have increased as a result of CO2 rising. You know, global average temperature measurements from thermometers have been available since 1880. Since 1880, which is 137 years, we've had continuous global reliable measurements of temperature from thermometers around the world. Before that, there just wasn't enough global continuous coverage. So we had to rely on indirect measurements of temperature, proxy measurements like ice core data, tree ring width, and coral reef isotope data. But since 1880, you can average all of the global temperature measurements over the entire course of a year and come up with a global average temperature. And this is dealing with the surface data, surface temperature. And if you did that, you'd find out of all the years since 1880, so that's what, 136, 137 years, 2015, last year, was the warmest on record. And the second warmest year on record was 2014. This is not an isolated event, where these two are not isolated events. 9 of the 10 warmest years have occurred since the early 2000s. Okay? So global temperature measurements are rising. We'll be looking at more when we talk about climate change in the class. But CO2 is a driver of increasing temperatures because of the enhancement of the greenhouse effect. And these CO2 levels are unprecedented. And this figure illustrates that. Recently, CO2 concentrations have increased above 400 parts per million for the first time. In May of 2013, daily CO2 concentration exceeded 400 parts per million for the first time at Mauna Loa. In April of 2014, monthly average CO2 concentration at Mauna Loa exceeded 400 parts per million for the first time. And 2015 became the first year to have an average CO2 concentration above 400 parts per million. You can say goodbye to CO2 concentrations below 400 parts per million, folks. Okay? It won't happen again at Mauna Loa. And last time we were at this level, human life did not exist. Humans have been only around in our current form, Homo sapiens, for about 200 to 250,000 years. Okay? So before this point here in the figure to the left, going back 800,000 years, there were no humans. Okay? So this is obviously the highest CO2 concentrations have been during human time. In fact, going back much farther than that, or further from that than that. By 2100, CO2 concentrations would be anywhere from 550 to 970 parts per million, depending on the decisions we make now and in the coming years in terms of emissions. Mentioned how burning of coal for power generation emits CO2. It also can emit CO, carbon monoxide, SO2, sulfur dioxide, and NOx, nitrogen oxides. Carbon monoxide is important because when levels get too high, it can cause health effects. You might have seen or had a carbon monoxide sensor in your home. Okay, a very sad way to commit suicide is to be in your garage, in your car, and then turn the car on and have this carbon monoxide come out of the tailpipe and have the garage door closed and stay in your car for a long time, because then the carbon monoxide levels build up and then you can have issues, right? Now let's talk about air pressure and air density. Baseballs travel farther in higher altitude air, such as Denver, Colorado, where Coors Field is, the Mile High City. That's among the top offensive ballparks each year. It's been like that ever since it opened in the late 90s. Okay. For money reasons, not only does the ball travel farther, as it says here, in higher altitude air, so there's more home runs hit there. But, what was done was that the fences were moved back. There were too many home runs being hit in that ballpark. So the fences were moved back, but that caused a bigger outfield, so now more balls fall in between the infielders and outfielders because they move the fences back, okay? So you try to compensate for the greater, more traveling fly balls by, causing the home runs to have to go farther, but then you open up more space in the outfield for balls to fall in. Air density. Let's talk about air density. What is air density? Okay. And how does it vary in the atmosphere? Well, air molecules are held near the surface by gravity. Okay, the force of gravity, which is strong and invisible, pulls down on the air above and squeezes the air molecules close together to the surface, compresses them. And this compression causes their number in a given volume to increase. Air density, given by the Greek letter rho here, is the mass of air molecules per given volume or space. So air density is mass of air per or divided by volume. Air density is highest at the surface. Near sea level, air density on average is about 1.25 grams per cubic meter, and it decreases with height. And I'm sure you've noticed this, right? If you go hiking in the mountains, it can be harder to breathe. And you notice the effects as you ascend in altitude, right? Your ears pop. You can feel wheezy, okay, because of the effect of lower air density, okay? It's harder you don't breathe in as much oxygen. Even though the concentrations of nitrogen and oxygen remain about the same in terms of percentage up to 50 miles, there's less molecules, lower air density, so you breathe in fewer molecules as you go higher up. There's a reason that hikers of Mount Everest bring oxygen. How is atmospheric density different from atmospheric pressure? The weight of air molecules acts as a force on Earth's surface, as well as humans and other living and non-living matter on the surface. Air pressure, or atmospheric pressure, is defined as the amount of force exerted over an area of surface. And that force is basically weight. So you can think of air pressure as the weight of air per unit area. The pressure at any level in the atmosphere can be related to the total mass of air above that point. The greater the amount of mass above a point, the greater the amount of weight, and the greater amount of weight per area, or air pressure. Air is surprisingly heavy. The weight of all of the air around the Earth, okay, if you had a magical scale and you were able to weigh the entire atmosphere, it would be about 5,600 trillion tons. It's 5,600 trillion times 2,000 pounds, okay? And a column of air, 1 square inch in area, extending from sea level all the way to the top of the atmosphere, would weigh 14.7 pounds. It gives you a perspective on the greatness of air pressure. If you have an air column, just 1 square inch in area, okay, so that's what? The size of a postage stamp, right? Very small. And that would be at sea level, there's 14.7 pounds of air weighing down on that very small 1 square inch. Okay. Sea level is basically as you could surmise, the average height of the ocean surface. I have a question for you. If air pressure is so great because of the weight of air on Earth's surface, then how come humans aren't crushed by this pressure? it's because humans are exerting an equal force outward, okay? So air pushes down on us, but we push back out on the air, okay? Now, if you went to a planet like Venus, which has a much more massive atmosphere and therefore greater amount of air pressure, there you could be crushed. There's multiple reasons that a human could not survive at the surface of Venus. One being the average surface temperatures of 896 degrees Fahrenheit. Another being the fact that there's no oxygen in the atmosphere. And another one being the weight of the atmosphere. Now, not only does air density tend to decrease with height, but air pressure always decreases with height. Remember this. As you ascend, as you go upward in the atmosphere, okay, air pressure will always decrease with height. It also always increases with descending height. And here's a figure from the book, figure 1.7, showing how air pressure and air density decrease with height. Notice that owing to the fact that the air near the surface is more compressed due to gravity, air density normally decreases rapidly and then more slowly as you move farther away from the surface. So, in fact, the decrease in air density and air pressure with height is not linear. It's more exponential. Okay, the density and pressure decrease very rapidly at first and then very more slowly as you go higher and higher. And this figure shows, it gives you a sense of decreasing density visually with height. This is supposed to be a 1 square inch area, and here's a scale, and there's 14.7 pounds of air molecules weighing down on that 1 square inch. A chemist would have issues with this figure because molecules are represented by these white spheres, of course, or many types of molecules. Their geometry is a lot more complicated. They're clustered together, but that's fine for getting us just visualizing the sense of air density with respect to altitude for us meteorologists. Now, if more molecules are packed into a column of air, what happens to density? It increases, right? Remember what air density is, mass of air per volume. And the thing is, air molecules are what makes up air mass. The more molecules in a column, the more mass, okay? Everything's made up of molecules, right? You, me, the surface, your cat, if you have one, or if you have a dog, okay? And so if you put more molecules of air into a column and you don't change the thickness or the area of the column, the density will increase, okay? And what happens to surface pressure? It also goes up because more air in the column means greater mass, greater weight per area, greater pressure weighing down on the surface. Conversely, if there are fewer molecules in the column, you take air molecules out of a column, and again, you don't change the area of the column. Let's say it's still 1 square inch, and it still goes from the surface, sea level, to the top of the atmosphere. Well, the air would weigh less, okay, lower air density, less weight of air on the surface, and the pressure goes down. In order to talk about pressure, we need to talk about units, what we measure it in. And most common units for atmospheric pressure are the millibar, abbreviated as MB, and the hectopascal, abbreviated as HPA. These two units, millibar and hectopascal, are the same, equivalent. 1 hectopascal is the same as 1 millibar. Another unit used is inches of mercury, or inches of Hg. A lot of the chemical symbols are nice because they're intuitive. Okay, like carbon has a chemical C, hydrogen has the chemical symbol H, oxygen has the chemical symbol O. But some of the symbols are based on I think the Latin or either Greek names. And so mercury doesn't have a symbol of, say, M or Me, it's Hg. Okay. And in fact, for meteorologists, people who study weather, we generally look at pressure in terms of millibars. We're analyzing weather maps. But for the general public, pressure, atmospheric pressure, or air pressure tends to be analyzed in inches of mercury. Okay, so when you watch the Weather Channel local forecast, when you check your Weather Channel app, they'll show you pressure generally in inches of mercury. And that's basically the height of a column of mercury at the surface. Okay, it has to do with the mercury barometer. In general, at sea level, the standard value for atmospheric pressure is 1013.25 millibars, 1013.25 millibars. And because millibars and hectopascals are equivalent, 1013.25 millibars equals 1013.25 hectopascals. And this is just under 30 inches of mercury, 29.92 inches of mercury. Okay? So when next time you look at your Weather Channel app or Yahoo Weather app, look at the pressure. If it's less than 29.92 inches of mercury, then the pressure is lower than average sea level pressure. If it's greater than that, then the pressure is higher than the average pressure at sea level. Typically, the range of pressures on the surface of Earth is 950 to 1,050 millibars. 950 to 1,050 millibars. That's 28.05 to 31.0 inches of mercury. Okay. And then, like we mentioned, with respect to the mercury barometer, the instrument that's used to measure pressure is called the barometer. Okay? Not like the pressurometer or something. Barometer is used to measure atmospheric pressure. The name actually comes from the fact that another unit of pressure is bars. And you might understand this if you look at millibar. Okay? Millibar. There's 1,000 millibars in one bar. And here's figure 1.8. Another figure from the book showing how atmospheric pressure decreases with height. And this one's kind of more close to the surface, and it has a real-world example of Mount Everest in it. You know, you only need to go up to 5.5 kilometers, which is about 3.5 to 4 miles, in order to be above 50% of the surface, okay? So you really don't need to go very high in the atmosphere to be above half of all the molecules, okay, in the atmosphere. As one approaches the height of Mount Everest, about 9 kilometers or 30,000 feet, the air pressure would be about 300 millibars. And if you compare 300 millibars to the average sea level pressure of just over 1,000 millibars, that tells you that one would be above about 70% of all the molecules in the atmosphere. Okay? So again, there's a reason that one needs to carry oxygen to ascend. There's a reason why the upper part of Everest is known as a danger zone, because if you're near the summit too long, because the pressure is so low there, the air density is so low, your brain can quickly become oxygen starved. When one is about 9 miles above the surface, he or she is above 90% of all the air molecules. By the time you get to 19 miles, you're above 99% of all the molecules. Notice, air pressure decreases more rapidly at first and slower with height as you go higher. Atmospheric pressure becomes lower and lower until eventually the atmosphere merges with outer space where there's no air molecules and hence no air pressure. Now, the vertical structure of Earth's atmosphere is complex. By the way, really nice picture here, right? Looks like an ocean. Here's a cumulonimbus cloud. You have an anvil top. You have a darker shaded region here where rain is falling. This is called a rain shaft. You also have the coloring of the sun here. The effects of the sun on the coloring, kind of a nice light red-orange shade. You also see the reflection of sunlight here in this bright region at the top of the cumulonimbus cloud. But coming back to the Earth's atmosphere, the structure of it's complex. The atmosphere is composed of different layers. There's 4 layers of the atmosphere. And they're based on temperature. That's how they're defined. Okay. So the vertical temperature profile indicates 4 layers. And we'll be going into detail about the properties of each, where they are found, and so on. The 4 atmospheric layers are the troposphere, the lowest layer of the atmosphere, the stratosphere, second layer of the atmosphere from the bottom, third layer of the atmosphere from the bottom is the mesosphere, and the top layer of the atmosphere is called the thermosphere. By the way, how do we measure the vertical structure of the atmosphere? How do we determine how temperature varies as we go up in the atmosphere? Well, we use a weather balloon, okay? Here's a weather balloon called a radiosonde balloon that was about to be launched by a San Jose State University graduate student of meteorology, Scott Strenfel, in July of 2008. And attached to the weather balloon is an instrument package. This is called a radiosonde, okay? The radiosonde is a collection of instruments, including a thermometer to measure temperature, barometer to measure pressure, wind instruments, okay, humidity instruments. Coming back to this figure, the vertical structure of the atmosphere with respect to temperature is complex. The Earth's average surface temperature is 15 degrees Celsius or 59 degrees Fahrenheit. And as one ascends, moves upward in the troposphere, the lowest layer of the atmosphere, temperature decreases with height, as you can see here. By the time you get to the top of the troposphere, called the tropopause, which divides the troposphere and stratosphere, average surface temperatures are down to around minus 75 degrees Fahrenheit. Okay, very cold indeed. Nearly all weather occurs in the troposphere. Here you see a cumulonimbus cloud, a thunderstorm cloud, its base in the lower part of the troposphere, and its anvil top at the top of the troposphere. And then you see temperature stays relatively constant in the lower stratosphere before increasing with height. Okay, temperatures get near freezing point again in the upper stratosphere. And then temperature begins decreasing with height in the mesosphere. The coldest temperatures in the Earth's entire atmosphere are found at the top of the mesosphere. Here you can find more meteors before they burn up as they get into the stratosphere. And then temperature begins increasing with height again in the thermosphere. We're going to go into each of these layers in detail. Okay, let's start with the troposphere. It's the lowest layer of the atmosphere, and it's where almost all weather occurs, okay? Occasionally, cumulonimbus clouds can overshoot the tropopause and extend into the stratosphere. And there are a few clouds, like polar stratospheric clouds and noctilucent clouds, which can be found in the upper atmosphere above the troposphere. But almost all the weather is there. The troposphere is well mixed. It's kept well stirred by rising and descending air currents. It's common for air molecules to circulate through a depth of more than 10 kilometers, 6.21 miles, in just a few days. The depth of the troposphere is from the surface to about 11 kilometers, 36,000 feet, near cruising altitude, depending on the airline and the weather. And this depth does vary. This is the average depth, but in the polar regions where it's colder, the troposphere is thinner, okay? Because the colder air is more dense, and so the air molecules are closer together, and you don't have to go up as high to reach the tropopause. In the polar regions, the depth of the troposphere can be as low as 8 kilometers, whereas in the tropics, okay, near the equator, the depth of the troposphere may reach 15 kilometers. But the average depth is 11 kilometers. Air usually cools with decreasing height. This decrease in air temperature with increasing height is mainly because of sunlight warming the Earth's surface, and the surface in turn warming the air above it. Temperature lapse rate is the rate at which air temperature decreases with height. And the average lapse rate in the troposphere is 6.5 degrees Celsius per 1,000 meters, or 3.6 degrees Fahrenheit per 1,000 feet. That means for every 1,000 feet you go up, you ascend in the troposphere, you can expect air temperature to decrease by an average of 3.6 degrees Fahrenheit. Okay? It gets colder as you go higher up. I'm sure you're familiar with this. If you go to the mountains in winter, there's a reason that it doesn't snow much near sea level in California, but it snows a lot in the Sierra Nevada mountains in California. And keep in mind, this is only an average. On some days, the air becomes colder more quickly as we move upward, which would increase or steepen the lapse rate. On some days, the air temperature decreases more slowly with height, and the lapse rate would be less. Occasionally, the air temperature may increase with height, producing a condition known as a temperature inversion, okay? Because it's inverted to what the normal pattern is of temperature decreasing with height. And when this happens, it can trap pollution below the inversion, within the inversion. And so the lapse rate fluctuates, depends on the time of day, the season, okay? The troposphere name comes from the Greek tropin, which means to turn or to change, and that references the air currents that ascend and descend in the troposphere that keep it well mixed. The next layer of the atmosphere, as you ascend, is the stratosphere. It has a depth of 11 to 50 kilometers. Okay, so it is significantly deeper than the troposphere. And in the stratosphere, air warms with height. Okay, with the exception of the lowest few kilometers where air's temperature is isothermal with height, it doesn't change with height. But then air begins increasing with height, and this prevents mixing. So unlike the troposphere, the stratosphere is not well mixed. The name stratosphere comes from stratified, okay? And the temperature inversion prevents mixing because as the air rises, if the air were to rise, it would rise in even warmer air, and so the air would be colder air rising into warmer air, and it would sink back down, okay? It prevents mixing. And the ozone layer is found from about 20 to 30 kilometers. There's ozone throughout the stratosphere, it turns out, but the peak ozone concentrations, the ozone layer, is found from 20 to 30 kilometers in the middle part of the stratosphere, basically. And the ozone layer absorbs ultraviolet radiation from the sun, as we've talked about. Even though the air temperature increases with height, the air in the stratosphere tends to be very cold, okay? You might be wondering why temperature continues to why temperature increases with height in the stratosphere, right? It's because of the ozone. The ozone, unlike other molecules in the troposphere, is able to absorb ultraviolet radiation from the sun. So the ozone in the stratosphere absorbs UV from the sun, and that heats it up. Okay, and the reason the temperature increases with height is because the ozone, as you go higher and higher, the ozone is at higher altitudes in the stratosphere is more efficient at absorbing UV radiation from the sun. So you have more efficiency and greater warming in the upper stratosphere than the lower stratosphere, and so temperature increases with height. The third layer from the bottom is the mesosphere, home of the coldest temperatures in the atmosphere. It has a depth of 50 to 85 kilometers. Mesosphere means middle sphere. And the air in the mesosphere is extremely thin and the atmospheric pressure is very low. Okay, and so because of that, there's very little oxygen as a result. Okay, the brain would become quickly oxygen starved or go into hypoxia at these altitudes. Even though the percentage of nitrogen and oxygen in the mesosphere is about the same as the surface. At the surface, 78% nitrogen, 21% oxygen, both diatomic. A breath of mesospheric air contains far fewer oxygen molecules than a breath of tropospheric air. Temperature decreases with height, and again, the coldest atmospheric temperatures are found in this layer, specifically at the top of the mesosphere. The average temperature at the top of the mesosphere is minus 90 degrees Celsius or minus 130 degrees Fahrenheit. For reference, the coldest temperature ever recorded on the surface of Earth was at Vostok, Antarctica, July of 1983, I believe, and it was minus 128 or minus 129 degrees Fahrenheit. So the average temperature at the top of the mesosphere is colder than the lowest temperature ever recorded at the surface, to give you perspective. The lowest temperature ever recorded in the atmosphere, not at the surface, was minus 243 degrees Fahrenheit, found at an altitude near the top of the mesosphere, lower thermosphere, over Alaska in 1966. Okay? Occasionally, temperatures at the top of the mesosphere can be as minus 250 degrees Fahrenheit. Okay, basically unimaginably cold, right? The thermosphere is the next layer of the atmosphere, the top layer of the atmosphere, right? The last one before you get to space. And it has a depth of 85 to question mark kilometers. Why do you think there's a question mark there? Okay, do we know the true top of the thermosphere? Not really. There's no true lid, okay? You can't, there's not a point where you're in the thermosphere and then you move an inch up and you're in the space. It thins to space, but there's no true top, okay? Temperature increases with height in the thermosphere. And the reason for that is because of the density of air up there, okay? There's basically no air in the thermosphere. You're above almost all the air. So the actual density of the air, any air, it's very low. There's great spacing between the molecules, okay? Remember, air density is mass of air per volume. The greater the spacing between the molecules, the lower density. So the molecules are greatly spaced. Low density of the thermosphere means that air molecules move an average distance of about 1 kilometer before colliding with another molecule, whereas a similar air molecule at the Earth's surface would move an average distance of less than 1 millionth of a centimeter before it collides with another molecule. So the molecules are greatly spaced, so they move fast. Okay, they're very independent, so they're able to move fast, and that leads to a apparent high temperature. We'll talk more about it in the next next two lectures, but temperatures are really a measure of the average movement of the molecules. The faster they move, the higher the temperature. Okay. Temperatures exceed 100 degrees Celsius or 212 degrees Fahrenheit once you get above about 75 miles above the surface or 120 kilometers. Okay, but and why is this temperature important? It's the boiling point of water at sea level. You wouldn't necessarily feel hot though. Okay, even though the temperatures are apparently so high because the molecules are just speeding around rapidly, you would still, when you're protected from the sun, you would still feel cold. Why? The reason is because there's too few molecules in this region to bump against something like exposed skin and transfer enough heat to feel warm. Okay, so the molecules move very fast, but there's just not enough of them to really to make contact with you and warm you up. Okay, moving along. We've now covered the atmosphere. We've covered the 4 layers, properties of the atmosphere with respect to density, pressure, and temperature. And the remaining part of the lecture looks at kind of an overview of some more topics we'll cover. Topics we'll cover in more detail throughout the as we go forward through the semester. Here's a figure showing the 4 major scales of atmospheric motion. We have the microscale, weather phenomena on the order of 2 meters, the mesoscale, phenomena on the order of 20 kilometers in size, synoptic scale, phenomena on the order of 2,000 kilometers, globoscale, phenomena on the order of 5,000 kilometers. And the greater the scale, not only the larger the size, but the longer a phenomenon lasts. Okay, so on this figure, the smallest atmospheric phenomena are turbulent eddies. Okay, these are those tiny circles or rotations of wind that you see blowing around leaves. Okay, on the ground. And these are only on the order of a few feet in size, and they last for a few seconds to maybe a few minutes. Not all of these weather phenomena are on one scale. Thunderstorms and tornadoes and water spouts, weaker tornadoes over water, along with dust devils, may be on the mesoscale or microscale. Okay. And features of the mesoscale last from minutes to hours. We have different wind types here, wind patterns, like land and sea breezes or offshore and onshore winds, okay, mountain and valley breezes, Chinook winds in Colorado, Santa Ana winds in Southern California, Diablo winds in the East Bay. They last for hours to days, okay? They're on the scale of 20 kilometers in size. Then we look at some of these larger scales of atmospheric motion, or larger phenomena. Hurricanes and tropical storms will last for days to weeks, okay? And they're getting larger and larger. By the time you get to long waves in the jet stream, you're dealing with global scale phenomena, which are about 5,000 kilometers on average in size, and they can last for weeks. Alrighty. Let's look at a weather map for the first time in this class. And before we do that, it's important to make this note about wind, which we mentioned before, but we'll mention again to review. Winds are referenced by the direction they are coming from, not going to. Okay? Remember that. And fronts are boundaries that separate air masses with different temperatures. You may have heard of a front, okay? Cold front, warm front. It's a boundary between basically two different large three-dimensional volumes of air masses, that have different temperature properties. And they're described by the air mass that's doing the motion. We'll talk more about this when we get to fronts in chapter 8. But a warm front would have the warm air mass doing the moving into the cold air mass. A cold front has a cold air mass moving into a warm air mass. And they're drawn by lines with colors. And on a weather map, an L represents low pressure. And it's drawn in red. Whereas an H shows an area of high pressure. And the H is shown in blue. And low in the atmosphere, generally, low pressure at the surface tends to be associated with active weather, precipitation, okay. Whereas rising air, okay, forming clouds and precipitation. Whereas high pressure tends to be associated with sinking air and therefore cloud-free skies, boring weather, okay. Let's look at the weather map. Here it is. This is a weather map from the book. And there's a lot on it, okay? And you'll become more familiar with this reading one of these as the semester goes on. But I'd like to point your attention first to this red L. There's an area of low pressure over northern Minnesota, okay? And extending southward from that area of low pressure, or southeastward, is a front. See this purple front with the alternating semicircles and triangles? That's a occluded front, okay? And then this occluded front extends southward through western Wisconsin. And as you get into northern Illinois, the front separates into a warm front, which extends through southern Illinois into Tennessee and northern Mississippi and Georgia, and a cold front extending into Missouri and then moving westward into Oklahoma, northern Texas, and even into Colorado. Okay, the green shading represents precipitation occurring. Okay, two semicircles are showing light rain here in northern Minnesota. We also have some showers in southeastern Missouri. By the way, this red symbol here shows a thunderstorm. Okay, one's occurring west of Chicago. You'll also notice the blue H's. Here's a blue H in southern Canada, or Canada. Here's a blue H in western Pennsylvania. High pressure. Sinking air, boring weather. Notice no precipitation, no fronts, okay, occurring with the highs. Okay. Then we have these numbers. As you might be thinking, these numbers are showing temperatures. Okay, so here's a 61 in Central Oregon, 81 in Fresno, perhaps, 69 in North Central Nevada, 86 here in this could be Prescott, Arizona. Warm south of the cold front. Okay, see the 83 in southern New Mexico and the 82 here near San Antonio. But then if you go north of the cold front, 50s in Colorado and Kansas, or 40s further north into Wyoming and Nebraska. Okay. And you also see 80s here along the Gulf Coast. See these barbs connected to the circles? Okay? Those are wind barbs, and they show you not only wind direction, but wind speed. The direction that the barb extends from the circle shows you the direction the wind's coming from. Okay? So for example, in Central Oregon, see how the wind barb extends eastward from the circle? It's an east wind, okay? And in these three weather stations, in Denver, this one in somewhere in Wyoming, and this one in Montana, you have north northeast winds. Okay, and the speed, okay, is given by the flag. Okay, the tick. Longer tick means 10 knots, about 11 or 12 miles per hour, and shorter tick mark means 5 knots. Okay, so here's what would this wind be here in Fresno? It's coming from the southeast at about 10 knots. Okay, and what's sometimes done on these weather maps to help the viewer visualize the sense of the wind flow is to draw streamlines. They're basically lines that show the larger scale winds over an area. So out of this high pressure system here, we generally have clockwise movement of air. Same with this one over Pennsylvania. And this low would generally have counterclockwise moving air, okay, which you can kind of sense if you examine the winds around this low. Okay, see that counterclockwise sense if you look at the wind barbs. And in the northern hemisphere, low pressure at the surface is associated with counterclockwise movement of air and inward flow of air to the center. High pressure, on the other hand, is associated with clockwise and outward movement of air from the center. We could take a step back, look at a larger picture from space, and look basically at a satellite image, okay? And here's our low pressure system with the fronts, okay, drawn. And you see the cloud cover, okay, and not surprisingly rain below it, okay. You see other areas of clouds in the U.S., okay, maybe some thunderstorms in Florida, okay, some few clouds in California. Here's a hurricane in the eastern Pacific, okay. We'll be talking about how satellites work in the class, okay. Here's a figure from the book showing an ice storm near Oswego, New York. And the ice is very heavy, okay? Mind you, when the ice falls and it's heavy, it weighs down whatever it coats. So the ice was causing the power lines to sag, and it even was causing these poles to basically move down at an angle. Okay, if it got heavy enough, it could cause the collapse of the poles and the lines. And to finish off the first lecture, here's a really beautiful photo in a way from Eric Nguyen showing a tornado and a rainbow basically side by side in the same photograph over south central Kansas during June 2004. Okay, here's a building, looks like a house, and here's a tornado, and you see the debris it's picking up, okay, behind, and you see the rainbow in the background. Okay, that's it for lecture 1.